Good afternoon, everyone, and thank you for participating in this webinar. I am Vishal Kumeta, and I'm an assistant research professor at the University of South Florida Center for Urban Transportation Research, or CUTR, and I'll be presenting the findings on behalf of the research team today. This webinar presents results on the project entitled Proactive Congestion Management. First, I would like to take this opportunity to thank the core research team, which includes the principal investigator, Dr. Cecilio Concas, who is also the program director of the Autonomous and Connected Mobility Evaluation Group at CUTR, Center for Urban Transportation Research, USF, and Dr. Mohsen Kamrani, and also the project sponsors, which include the National Institute for Congestion Reduction, NICR, and the Tampa Hillsborough Expressway Authority, THEA. Also, the project was performed in collaboration with the Texas A&M Transportation Institute, and we would like to thank them for their support. This slide basically presents the outline of this webinar today. And what we see is we're going to start with a quick research overview, followed by the literature summary, then brief touch on the methods followed, and this is followed by a discussion of the development and validation of the core concept here, which is the congestion detection algorithm. And then we discuss how the algorithm can be used in conjunction with microsimulation models to test mitigation strategies that can be deployed in real time. The conclusions or key takeaways and recommendations are presented after. To give a quick overview, the main goal of this project was to develop a congestion detection algorithm that utilizes conventional and new traffic data sources, such as connected vehicles, even in their infancy and with low penetration rates, which means low presence within the traffic volume, to detect and distinguish congestion levels in real time. The idea was to ensure that in the era of various sources of data, the gradual transition of the data sources from conventional measures, such as your radar detectors or Bluetooth detectors, to more granular sources, such as connected vehicles, which you can get up to 10 data points every second, would not hinder the algorithm's capabilities, providing reliable congestion estimates and with minimal computational needs. And more specific objectives include identifying congestion types from any data source, validating using real-world scenarios, and simulation of mitigation strategies to try and combat the level of congestion experienced within a specific study area. In short, just to give a brief summary of the literature, what we see is that several researchers have attempted and illustrated the pros of real-time congestion detection. However, most of these approaches do not incorporate known real-world limitations, such as the penetration rates and dead signal zones, and even data gaps that exist with live data sets. And some of the methods that were followed are shown on the slide: static thresholds of speed and density, Kalman filtering for density estimation. We have neural network models capturing speed and headway variations. Researchers have used support vector machine models coupled with fuzzy logic metanet models, and also automatic incident detection algorithms. What we noticed is that overall, in most detection classification methods, the prediction accuracy drops significantly with data gaps or low penetration rates, and this can severely impact the accuracy of these tools. Now, for this research, we start by compiling data fusion, so compiling the data sets, right? So the research utilized two sets of data obtained from two locations. We have the conventional data that was obtained from Texas, and it involved radar and anonymous wireless matching for travel times, radar for volume datasets. And then we had the connected vehicle datasets from Florida, which were part of the Tampa CV pilot study. The Tampa CV pilot study involved over 1,000 participants within traversing the Tampa downtown area, and they were provided with onboard units, and the vehicles were transmitting these trajectories over the air and into the roadside and on to the roadside units, which then send it to the server to collect these data sets. The figure here to the right depicts the research flow and data fusion of various elements, including travel times, speeds, incident records, and weather. The Texas dataset was mostly used for training due to more segment diversity and completeness, while validation was performed on the connected vehicle dataset from Florida. And then microsimulation models were also calibrated to test potential congestion mitigation strategies that could be applied to recurring versus non-recurring congestion occurring in this area. To give more specific properties of the study sites, here is an example where we have data from 13 roadway segments that was used. To be specific, 3 segments were from Tampa's CV pilot and 10 in and around locations close to the Houston area in Texas. This was chosen due to compatibility and also data availability from the project partner who supplied us with these data sets. The segments were all selected due to them being very close in nature, and they had similar traffic properties. All segments, as you also see, had similar lengths and speed profiles and geometric properties like ADTs or the percentage of heavy vehicles, very similar in composition, but also the lengths ranged between 2 kilometers and 3.2 kilometers. Now, getting to the congestion detection algorithm that was developed, the algorithm itself utilizes travel time indices to establish congestion thresholds. As shown in the travel time index density plots to the right, which is TTI, individual segments have varying speed profiles due to location and commuting behavior, making static thresholds difficult to implement, especially saying if a TTI of 1.3 in one segment indicates congestion, it's not necessarily that the same 1.3 would indicate congestion in another area, which is usually heavily traversed. So to combat this issue, we utilize the percentage change in travel time index at each time point to establish a B1 metric. After utilizing this metric, the B1 density plot shows the sink in distributions, as you can see to the right of this, the B1 density plot. This metric can then be used to filter congestion by various types and without the need for focusing on individual segments. So the metric itself becomes thresholds that are independent of the segment. Now, then we utilize signal processing to further clean the variability in the B1 metric observed due to data gaps and also changes in granularity. As you see in the figure below, the Butterworth filter, which is an infinite impulse response filter, commonly used in voltage applications, is used to clean the signal to identify congestion peaks. And this generates the red profile line that you see, which consists of peaks signifying the onset and potential intensity of the congestion. So the height of the peak determines the intensity of the congestion, and the location of when the peak starts to occur gives you an indication of congestion is about to begin. And this happens before actual peaks are determined from the data set itself. Now the figure here shows the thresholds developed from the Butterworth filter applied to the B1 metric. In essence, each level signifies a type of congestion. And here, for example, below 0.03 being typical congestion or normal as you call it, and peaks observed above the 0.17 threshold indicates a potential incident level event that could have occurred. We also noticed that typical congestion, recurring congestion generates similar thresholds to congestion caused from weather events such as rainfall. And this makes it a bit difficult to discern what's happening at level 2. Other non-recurring congestion include presence of work zones or road closures. After developing the algorithm, we need to validate and see if the algorithm is generating similar performance in other areas. So we used the connected vehicle datasets from Florida to test the algorithm. And we test the normal conditions and any signs of congestion using 2 approaches. The developed algorithm is able to predict normal conditions where no congestion is detected with a very high accuracy and recall of up to 0.96. We also test instances of incidents by comparing the congestion algorithm output with police reports of approximate incident start and clearance times. Overall, the algorithm was able to achieve a mean prediction error of slightly above 30%. The algorithm itself was accurately predicting incident events 70% of the time. And keep in mind that this is at least 2 to 3 time periods before the incident is actually recorded in police reports. The accuracy achieved here is similar to those observed in literature. However, we must consider the aspect of this algorithm was validated across multiple segments, geographical regions, and even data sources, adding to its robustness. Then we head to microsimulation. In order to test congestion mitigation strategies along the study area in Florida, shown in the first figure, that's the study area, we developed microsimulation models in Transmodeler. And 2 seed days, one for recurring and one for non-recurring congestion, were developed. Seed days being the days we used as the base for our calibration of the models. Now, due to access to high-frequency CV datasets, calibration of the simulation models was performed using travel times in a 5-minute time frame and in short 0.5-mile segments, as shown on the figure, from 101 to 115. The yellow dots indicate the length of the segments of 0.8 kilometers or 0.5 miles, where calibration was performed. And this is unlike traditional calibration using only volumes and one time period. Overall, we achieved a higher accuracy than what typical microsimulation calibration would. We used normalized root mean square error and mean absolute percentage error by comparing simulation generated travel times for each time period and segment to the connected vehicle observed real world travel times. The calibration was performed such that each segment did not exceed a goodness of fit of 30%, as shown below. So for recurring, we achieved a 22.7% NRMSE and 16.8% MAPE. The figures at the bottom show the 2 events that were modeled with recurring and non-recurring, and clearly the non-recurring was modeled after a crash. So that shows how high the travel time was during that period of the crash. In this slide, we present a video of the microsimulation calibration of the non-recurring incident, which involved the crash. And how we did this was the crash was simulated into the scenario by reducing the capacity at the recorded location by tapering and reducing the number of lanes in the facility. And this was done because typical microsimulation models don't account for crashes within their logic. And that's where the approximate crash location was. And then we can see how we can see the pattern in queue formation from this slide. And the propagation of the queue reaches all the way far back, indicating the extent to which the traffic was affected due to this non-recurring incident. Based on the algorithm predicted congestion time, we deployed countermeasures. But these countermeasures had to be deployed after assuming a 5-minute compliance period or time taken for all vehicles to start following the changes to the speed limits or dynamic message signs within the simulation. We tested 2 strategies based on algorithm prediction. The first one was speed harmonization, which involves varying the speed limits at specific intervals to change the behavior of drivers. And for this, we used the speed-based algorithm developed by Hale et al. 2016. We also tested dynamic rerouting by varying the rerouting volumes. The unique thing about this study area is the presence of reversible express lanes, which are on the upper deck of the highway. And because the crash happened on the lower decks, we're able to create a scenario where rerouting is possible to the upper deck to facilitate movement of traffic. The 2 strategies, dynamic rerouting and speed harmonization, were tested individually and simultaneously to correlate to the observed performance changes. And as you see, volumes were varied by 5, 10, and 15% for recurring congestion, and non-recurring we had 10, 20, and 30%. Now, this slide shows the space-time trajectory charts of the calibrated recurring and non-recurring congestion generated from the microsimulation output. With the deployment of mitigation strategies, especially both speed harmonization and dynamic rerouting, we observed notable decrease in the spread of the red circle, as you see on the right figures. This depicts the impact of the strategies on severe congestion scenarios, such as non-recurring. The space-time trajectories don't necessarily show much difference in the recurring, but there's slight improvement, as you can see by the density of the yellow dots, which indicate the level of travel time index and how it is being reduced back to normal conditions of 1. Now, compared to the no strategy, substantial change in flow is observed after mitigation measures were deployed. Now, here in this slide, we present the quantitative trends of travel time reduction as a result of the congestion mitigation measures. Speed harmonization by itself did not produce any significant reduction to the recurring or non-recurring congestion, as far as we observed, with maximum decrease of 1.6%, maximum decrease in travel time. However, when we deploy dynamic rerouting with respect to varying amounts of traffic volumes, for example, here at 15%, we produced the largest reduction in recurring travel times. For non-recurring, speed harmonization coupled with dynamic rerouting produced the best travel time reduction. And at the end of the day, the number of vehicles rerouted determines the mainline flow recovery. Although changes in mobility improvement are important, mitigation strategies would also have implications towards the safety of the roadway. And to showcase this further, we're going to take a closer look in the next slide. So for a closer assessment of microscopic behavior of individual vehicles, we plot the charts of the individual trajectories traversing the study area during the two types of congestion, while monitoring the effect of the strategies on speed profiles. As evident in the figures, speed harmonization resulted in lower peaks in speed profile when compared to the no strategy, which is shown in gray, compared to the dotted blue line. The peaks are reduced much further. This indicates decreased stop and go flow. Stop and go flow is typically associated with higher probabilities for rear end crashes, and reducing this is a significant improvement to the safety within this segment. While we see that dynamic rerouting has the highest impact on mainland flow, and this is expected due to the planned reduction in demand from diverting the traffic. Further, within the study area, coupling the two strategies results in the most mobility and safety benefits. So the key takeaways and recommendations from this project: the research focused on training and validating a proactive congestion detection algorithm using travel times. The output of the algorithm was used to test mitigation strategies in the microsimulation models. The detection algorithm in itself was effective in proactively predicting the onset of congestion and its 4 levels, with a mean prediction of error of slightly above 30%. A known limitation of this algorithm is the inability to distinguish between more than one congestion type occurring simultaneously. What we mean by that is, if we have recurring congestion with an incident at the same time, we're only able to detect the highest level that was observed. For example, it will be registered as an incident, even though recurring congestion is happening at the same time. And an interesting recommendation to practitioners from this project was the fact that connected vehicle segment-based travel time estimates to calibrate simulation models proved a lot more accurate in replicating real-world congestion than was initially anticipated. And this might be because of their ability to produce finer trajectory profiles and travel times within shorter segments. And that brings us to the end of this webinar. For more details, please refer to the published project report and journal paper, or contact us at the emails provided right there. And thank you for attending this seminar and webinar.